Hello, and welcome to a lecture on temperature and thermal expansion. This is very much an introductory lecture to get us used to dealing with ideas of thermodynamics, which is going to involve heat flow and the laws of thermodynamics, but this is a good starting point because, of course, temperature is one of the first things we think about when we think about thermal processes, right? Okay? All right, so let's get to our key terms. All right, so our first key term, no surprise, is the word temperature itself. What is temperature? Okay? Well, it's how hot or cold something is, right? We definitely know that, but that's, it's good to point out. That's simply what it is, okay? It is a physical quantity that is proportional to the average kinetic energy. That's the key idea. The average kinetic energy of particles in a substance. So if it's a gas, it's how quickly those gas molecules are bouncing around. If it's a liquid, how quickly, kind of sheets of the liquid are jiggling around. And if it's a solid, it's how much those locked in atomic nuclei within the lattice of the solid structure are jiggling, all right, vibrating. So that's the idea. That's what it is. It all has to do with actual kinetic motion. Now there's some complications to that because sometimes there's more than just kinetic motion. There can also be rotational motion. We've talked about rotational systems. Complex molecules can rotate, and additionally to just translating. We'll touch on that when we talk about some of the assumptions behind the ideal gas law. But the point being is that idea still holds true. Okay, it's a physical quantity that is proportional, not equal, to average kinetic energy. And it's important that it's proportional, not equal, zoom in a bit, because otherwise temperature would have units of what? Joules. But it doesn't. Temperature does not have units of joules. It's not an energy. It's just proportional to a particular average energy. Okay? In fact, the dimensions of temperature are new. All right? So we'll talk about the units of temperature, but if we're talking dimensional analysis, this is our fourth dimension that we have introduced. Because up to this point, we've had M for mass, we've had L for length, and we've had T for time. Those have been all of our dimensions. Every one of our derived units have been built on those three dimensions. And that has been totally sufficient to describe everything, the wide variety of physical processes, all the quantities, all the laws that we have discussed. Well, now we have a new one. This is brand new, okay? So temperature is represented by the uppercase letter phi. This is the Greek letter, and this is the uppercase version. Lowercase phi we're familiar with. It looks like that. All right, and that's just how we denote the dimension. Now, we don't use that very often. We're more interested in the units, but it's just so important to point out that physics has very few dimensions and everything is built on them. Case in point, we've only used 3 up to this point, and now we finally need a 4th, and that's it. That's all we will need for this introductory physics course. Once we get into electricity and magnetism, we'll need one more, a 5th and final dimension, okay? Okay, so the only absolute temperature scale is Kelvin. That's the one we'll be talking about the most, okay? But down in the key formulas, I'll point out the relationships between the other 2 big temperature scales. Okay, so that's temperature. Next up is something called the Zeroth Law of thermodynamics. Now, in a few lectures, you're going to see the first and second laws of thermodynamics, which are maybe have more that they can discuss. The second law introduces the idea of entropy, which is something that we've never touched on before, obviously, in our discussion of mechanics and gravity and so on. The first law is an energy conservation law, but one specific to heat flow. So these are big laws. They're fascinating. The zeroth law is kind of strange. Why do we talk about it first? Well, maybe because 0 becomes before 1. But why the name? Well, that's because historically it came after the first and second, and so it had to be given a name, so it was given the zeroth law. It's a pretty simple statement. It basically says that all heat is the same, if we're going to paraphrase it. And what that means in more practical terms or specific terms is the law states that if 2 systems are in thermal equilibrium with a third system, then they must also be in thermal equilibrium with each other. Okay? So it's the transitive property of temperature and thermal equilibrium. We'll talk about how thermal equilibrium is achieved. It's achieved through heat flow. Heat is a form of energy. More on that later. But now we just care about the fact that this is how we really define temperature between multiple systems, not just 2 systems. Furthermore, to tie it back into temperature, thermal equilibrium is defined as having the same temperature. Okay, so that's by definition, if 2 things are in thermal equilibrium, then they must have the same temperature, and vice versa. If two systems or objects have the same temperature, they must be in thermal equilibrium. Okay, okay. So here we have just the graphical representation of the zeroth law of thermodynamics. All right, and this is all like T equals, right? So the temperature between A and C is equal, and then so on, right? Okay, all right, so that's the zeroth law of thermodynamics, just something you want to kind of keep in your back pocket. Now, finally, a term that we're going to actually see put into practical use in the quantitative problems in this lecture is the coefficient of expansion. Well, what is that? Well, it's a material-specific okay, material specific value that tells how much a substance will expand or contract for a given temperature change. So we kind of know, right, that this happens. If you heat something up, it gets bigger. Obviously that's most pronounced in gases, but even solids, right? They do become marginally bigger. You can think of things that maybe don't fit very well when they're really hot, okay? Because I'm thinking more like metal joints and or even wood will expand a little bit when it's very hot. This causes creaking in homes, right? They're on a hot day, all the wood expands in a home, and then at night when it cools off, it creaks because everything is contracting. So the idea of expansion and contraction with temperature is intuitive, right? It's something we understand, something children understand, or we see in our everyday experiences. But here we're going to quantify it. All right. The units of the coefficient of expansion are either inverse Kelvin or inverse degree Celsius. And inverse, of course, just means 1 over, right? In the case of Celsius. So it does have units, the coefficient. Okay. And I bring this up because other coefficients we've seen, like friction, don't have units, right? Friction was dimensionless because it was just a ratio of forces. But not all coefficients need to be dimensionless. But there is something there that is in common, very much in common, between the coefficient of expansion and a coefficient like friction. And that is that it varies between substances, which is what that term material specific means. That means you have to look it up, right? So if I want to find the coefficient of expansion for lead, I'd look up a table of common coefficients of expansion, and there it is, okay? Likewise, if I want to find the friction coefficient between wood and Teflon, I'd look it up in a common table of coefficients of friction between substances. So these values have been collected and cataloged and then agreed upon in certain publications. All right, which means that they are all found experimentally, which is also called empirically. So these are all empirically determined coefficients, right? These are empirical quantities, which means they're not based on fundamental physical ideas. Instead, they're observations. Just to our best of our knowledge, this is the value. We don't know exactly where they come from necessarily. We can, once we describe, in the case of coefficients of expansion, the particular material properties, how like the crystalline lattice of the solid works, and the way the atoms interact between them, and intermolecular forces like the van der Waals forces, and electrostatic forces between molecules, and whether there are magnetic dipoles, and whether there's actually small scale mechanical processes that are happening, and what's the importance of imperfections, and with coefficients of friction, we care about things like the capillary force, and again electrostatic forces, and there's this incredible list of complicated phenomena that at the microscopic scale lead to these macroscopic coefficients. Okay, so they're very much just, to the best of our knowledge, this is the value, it works, let's use it. Okay. But it's messy, right? It's this interesting dichotomy in physics. We have this importance idea of building things off of first principles like Newton's laws and the conservation laws of energy and momentum, and then we have these let's just kind of use the best number that we can, for expansion, for example. So they're definitely very different perspectives, but they do get the job done, right? Whether we're building something of first principles or we're just doing the best we can with a number that we found experimentally. Okay, all right. So those are coefficients of expansion. Let's see how they show up in the formulas. So let's get down to our key equations. Okay, so we have a set of 3 key equations here that all refer to the relationship between the 3 temperature scales. And then we've got 3 equations that have to do with expansion of materials, or contraction for that matter, when they're being heated or cooled. Okay? All right, so first formula. This is just the formula that relates Celsius to Fahrenheit. Okay, so the idea is if you want to find the temperature in Celsius and you know the temperature in Fahrenheit, then you subtract 32 and then multiply that result by 5/9. Right? That's the conversion formula, and it's also not perfect, by the way. 5/9 is just pretty accurate, but it's not a perfect. This is not actually a perfect. This should be approximate, right? But it gets the job done. Now here's the thing: we really will never use Fahrenheit, but it's good to reference it because it is the temperature scale that we use in our everyday lives. It's a fine temperature scale for everyday lives. I'm not going to be high and mighty about temperatures and say we should only use Celsius to describe temperatures, because it's nice that it has a good range of human experiences of temperatures. Like 30 degrees and 100 degrees. That's a nice range. We can carefully describe what those different temperatures feel like. Okay, but it's not very scientific, right? Because the significance of 100 degrees in Fahrenheit is, what does it mean, right? Well, that takes us to Celsius. All right. Well, Celsius is a nice temperature scale because 100 degrees Celsius is boiling water and 0 degrees is freezing. But there's some problems there too, because first of all, it's boiling water at atmospheric temperature at sea level, or well, at a particular temperature, 20 degrees Celsius at sea level, with atmospheric pressure being what it is at sea level. So, that's kind of specific. It wouldn't apply to boiling water in space because basically water boils at, negative 60 degrees Celsius in space because the pressure is so low. And so, there's some universal problems there, right, about using Celsius, but it is good, again, for, scientific experiments in a typical lab because of its relationship to water. Now, here's the big one though, Kelvin, okay? Kelvin is the true absolute temperature scale. It's the one that really should be used most of the time in science because it is an absolute temperature scale. 0 degrees Kelvin is absolute zero. We'll talk about that more later when we talk about the ideal gas law. Furthermore, it's a temperature scale that is just well suited to a wide range of experiences. Very, very cold things where molecular motion almost stops to the temperature inside the core of stars that are undergoing incredibly hot nuclear fusion. So this is that one temperature scale that works for everything. And the way to relate Kelvin to degrees Celsius is to just add 273 to whatever temperature you have for Celsius. Okay. Now notice there's no multiplication because a change in 1 degree Celsius is equal to a change of 1 Kelvin. Okay, so if I go up 1 Kelvin, I have also gone up 1 Celsius, which is nice because sometimes we can talk about things and not worry if we're in Kelvin or Celsius. Notice how I mentioned that the coefficient of expansion either has units of inverse Kelvin or inverse degree Celsius. And that's because it doesn't matter, because a change in either of those temperature scales is identical. Okay, so anytime you have a formula that involves a delta T, a change in temperature, then you don't have to worry if you're doing it in Kelvin or Celsius. But you might as well do it in Kelvin because there's other formulas that only work in Kelvin. Okay? My students always ask me, should I use Kelvin or Celsius? Use Kelvin. There's one single time in a physics class that you have to use Celsius, which is the velocity of sound on Earth, which is based on Celsius. That's the only common formula that doesn't work with Kelvin. It only works with degrees Celsius. All the other ones, all the thermodynamic formulas work for Kelvin, and sometimes will work for Celsius, again, if there's a delta T. But if it's just a T, like T to the fourth, which we'll see in a certain formula, then that certainly will not work in degrees Celsius. Also note that when we talk about Kelvin, we say Kelvin, not degrees Kelvin. Not that it's terribly important, but if you want to get it right, you don't say degrees Kelvin. Okay, so enough about temperature. Let's get on to thermal expansion. All right, so this is the formula of linear thermal expansion. So this is change in length, hence the linear part, okay? This is the original length. This is the change in temperature. And alpha is the linear coefficient of thermal expansion. Units 1 over Kelvin, or Kelvin to the -1, or 1 over degree Celsius, okay? So that's alpha represents the linear expansion. So this is a material maybe that we don't care about its width or height, we only care about its length, then we would use this formula. Or maybe we don't care about its length, we only care about its width. If we only care about a single dimension of change due to temperature, then this would be the formula to use, okay? On the other hand, if we care about a volume changing, then we use the next one down. This is the change in volume. This is the original volume. Change in temperature, still change in temperature. And now we have a coefficient called beta instead of alpha, which is the volumetric coefficient of thermal expansion. Same units, okay? Now, if we want to relate beta to alpha for a given substance, beta is 3 times alpha, not alpha cubed, okay? And this can be proven, right? We won't do it here, right? But this can be shown that the relationship between the two must be that the volumetric coefficient has to be equal to 3 times the linear coefficient. Okay, so that's fine. That would be maybe, think of a block of metal, right? If I only care about it changing along one axis, then I would use my linear coefficient of expansion formula. On the other hand, if I care about the entire volume of the block changing, then I would use my volumetric relationship. When you look up coefficients of expansions for metal, you're really only going to find alpha, which means that you just take that value from a table of common coefficients of linear expansion and multiply it by 3, and now you've got your volumetric coefficient. Then you can use that for a volume increase for your metal block, okay? On the other hand, what about things that don't have a well-defined length or width or height, like gases, okay? Well, for a gas, you looked up coefficients of expansion, you'd only find beta values, and that makes sense because you can never expand that along a single axis, okay? All right, so let's get on to our examples. Okay, practice. All right, so there's 2 types of problems that involve linear or volumetric thermal expansion in comparing lengths and volumes, and type 2 problems that involve linear volumetric thermal expansion combined with other concepts, all right? So that's it, kind of it's the I decided to separate them as the simple cases where there's just a expansion or contraction, and then when there's something else going on. The one example I'm going to do that's type 2 is going to involve buoyancy, something we saw recently. Notice that there are no problems that refer to temperature because it's not really a standalone practice problem. If converting between temperatures, I expect you to know how to do it. Just use the formulas that I gave you on the last page. Okay, so example 1. A surveyor uses a steel measuring tape that is exactly 50.000 meters long. So very accurate relationship. And why would I have so many significant figures here, 5 significant figures? That's because thermal expansions are pretty small for most substances. They're sizable for gases, I guess. But for solids, there's not much going on, right? We're talking like tiny fractional changes, much less than 1%. And so that's why if we really want to see it, we better have a lot of significant figures. Okay? Anyway, so that is the temperature of this steel measuring tape at exactly 20 degrees Celsius. So that means that basically this tape was calibrated to be used at 20 degrees Celsius. And for very accurate tools, that's a common idea, right? So, but now we're going to use it out of its operating temperature range, but we're going to account for it. So the tape and its markings are calibrated at this temperature. What is the length of the tape when the temperature is 35 degrees? So what happens when you use it at 35 degrees? How long would the overall tape be? All right, so we're just going to use delta L equals alpha times L naught times delta T. And then I'm going to go ahead and solve for L. Look what I'm doing here. I'm going to say that L is equal to L naught plus delta L, right? And now this is the new length, right? And L naught is obviously the original length, and that's the change, okay? And so then I'm going to rewrite delta L as based on the formula from the key formulas. So I've just substituted it in. And then I'm going to factor out the shared term of L naught. So what we have here is actually a kind of a useful formula in its own right. We have that the new length is equal to the original length times 1 plus alpha times delta T. Because sometimes that's what you care about, right, is the new length rather than the change. And so maybe this is the formula that you want to use. But obviously it can be easily derived from the formula that's given in the key formulas. Okay? So then let's go ahead and find that new length, plug in our numbers. So the original length was 50.000. All right, this is the coefficient for steel, which was given here. It's a linear coefficient because we only care about a one-dimensional change. And here is our temperature change, which is 15, because we went from 20 to 35. That was a 15-degree increase in Kelvin as well as degrees Celsius. And so then we get, see, we needed all those sig figs because now our new measuring tape now is 50.009 meters long. So that means it got increased by 9 millimeters. It got 9 millimeters longer. Not a lot, but a tiny bit longer, okay? Now we could also come up with a percent increase, but instead we have an absolute increase here in meters or millimeters. Okay, so in part B, when it is 35 degrees, the surveyor uses the tape to measure a distance. The value she reads off the tape is 35.794 meters. What is the actual distance? Okay, so this is accounting for the fact that we're using this measuring tape at its non-calibrated operating temperature. Okay, so what we're going to find then is we're going to take delta L, all right? I'm going to find the change in length at this particular temperature, all right, which is, temperature increase 15, just like in part A. I'm going to use the same coefficient of expansion, but notice I'm not using the same length. That's because we're not using the whole measuring tape. And that means that it wouldn't make sense to put in 50 here because the change in length is only the tape that's being used, which in this case was just 35.794 meters of the tape, okay? All right, so that means that I have a change in length of 6.44 millimeters, definitely less than the 9, okay? Because again, this 9 doesn't always apply, right? If I only used 1 meter of the tape, it certainly wouldn't be 9 millimeters shorter, all right? Or 9 millimeters longer for that matter. It would be, some, whatever the fraction of that. It would be actually 1/50th of 9 millimeters, okay? If you were only using 1 meter of the tape, okay? So thus the actual length is L minus delta L, all right? And that's going to equal the original length, because the original length is the actual length in this case. So it would be the apparent length of 35.794 meters minus the change in length that we have accounted for due to the heat change, so 0.006444, or 644, all right? And that gives us 35.788 meters, okay? So see the difference? This is how long the tape appeared to be. This is how long it should actually be, okay? And again, appeared, I guess, is an interesting term. It actually is that length, but it's expanded, so we're just taking account of that expansion. Okay? All right, let's do another one. This one's going to involve a fluid, so something that's going to have a volumetric coefficient of expansion. All right? So a 200 cubic centimeter glass flask is filled to the brim with mercury at 20 degrees Celsius. How much mercury overflows when the temperature of the system is raised to 100 degrees Celsius? Okay? So here we have our linear coefficient of expansion for the glass, All right, this is again, you look it up in a table, and here is the volumetric expansion of mercury. All right, there you wouldn't find a linear coefficient of expansion for mercury because it's not a solid, it's a liquid. Okay, all right, so how do we go about doing this? So first of all, we are going to make an assumption that the flask is a minimal thickness. Okay, that means that when the glass expands, its volume expands. Effectively, that there's no increase in the thickness of the glass. Otherwise, there would be an expansion due to the overall shape of the flask getting bigger as the glass expands. But then as the glass expands, it also becomes thicker, which would then subtract some of that gained volume. Not all of it, but some of that gained volume would be subtracted out. We can do that. It's an extra complication. We have to kind of very carefully think about, is it expanding uniformly everywhere? Then we maybe have to think about the shape of the flask. So here we're just going to assume that the flask is really thin and it doesn't matter that the glass got marginally thicker. What does matter is that the flask holds more because the whole flask grows as the glass expands. All right. So what we're going to do then is find the change in volume of the glass, which is going to be the original volume of the flask, times the volumetric expansion of, or thermal expansion of glass, G for glass, times the change in temperature. All right. So here we have the original volume of the flask, 3, because remember, beta equals 3 alpha, right? So just take 3 times my alpha value that you pull out of the table, all right, and then times 80 Kelvin because we went from 20 to 100. Okay, so there we get our change in volume of the glass, right? Not a lot in terms of change in volume. Notice also I went ahead and converted over to cubic meters, all right? All right, so then we can continue on. This is the change in capacity of the flask. So then we're going to find the change in volume of the mercury because the mercury is expanding. Notice that mercury is a fun one to use because mercury actually has a very high coefficient of volumetric expansion because what's happening here with mercury is it just expands really easily, or at least more easily than other substances. Okay, and so then we start with the original volume of the mercury because it filled the glass right up to the brim, right? So it's exactly equal to the capacity of the glass. Here is our coefficient of thermal expansion. All right, and there's our temperature change. Okay, so there we have our change in volume of the mercury. Definitely bigger, right? 2.88, same order of magnitude as opposed to 1.92. All right, so then we just take the difference because how much spills is just equal to the change in volume of the mercury minus the change in volume of the glass, right? Because the glass can't catch up with the expanding mercury. So then we just take one minus the other, and there we go. That is how much spills, and we'll go ahead and convert that back to cubic centimeters, and then we find that 2.69 cubic centimeters of mercury spill. All right, we can do this with other substances. A common one is to do with like gasoline in a gas tank because the gas heats up, and will it still fit in the tank and so on. And so this is that idea of maybe gases or fluids expanding more quickly than the metal or glass container that holds them. All right, so hopefully that looks good. Let's do our third and final example. Okay. All right, so this one has some buoyancy involved in it, and in fact, part A is all review. So a block of lead with a volume of 0.45 cubic meters, so it's a big block of lead, and a density of 11,300 kilograms per cubic meter is floating in a pool of mercury. Back to mercury, right? And mercury has a very high density, much denser than the lead, which is how the lead is able to float in it, right? It's amazing to think of lead floating in something, but it would readily float in mercury because look, mercury is denser, 13,500, or a specific gravity of 13.5. Right? So part A, what fraction of the lead is submerged in the mercury? Okay, so this one, like I said, is entirely review. We could have done this back in our fluids chapter. So here's the picture with the forces and our floating lead in our tank of mercury or lake of mercury. All right, the fraction submerged is the part that's shaded. Okay, we'll just go ahead and do a sum of forces, buoyancy minus gravity, set this up, replace M of the lead with the density of lead times the volume of the lead, here described as object. All right, and then mercury is just described as fluid. Displaced is the volume of the mercury displaced. Okay, and then this is just continuing with our sum of forces. Then when we actually solve for the volume displaced, this term here, all right, and it's equal to 0 because it's an equilibrium. Any floating situation is equilibrium, right? That's why we have no acceleration. All right, and this, of course, is Newton's second law. So then anyway, we'll go ahead and solve for the volume displaced. The volume displaced has to be equal to the volume submerged because that's what we were asked for, what fraction of the lead is submerged. So then we'll go ahead and find the actual value, and we get 0.38 cubic meters. All right. And so then when we actually look at the fraction, we'll just take 0.38 over 0.45, and we find that 84, or you can think of as percent, 84% of the lead is submerged in the mercury. Okay, so again, review. All right. So now let's do part B. Part B is fascinating. How much would the system need to be heated for the fraction of lead submerged to increase by 10%? So a 10% increase from 84, 84% would, well, we take whatever 10% of 84 is, which is 8.4. So that would be plus 8.4%. And so then we ended up with 92.4% of the lead is submerged. That's what we're looking for, okay? And you can do it that way. I'm just going to do it as a change, okay? But it's good to remember that a 10% increase from 84 isn't 94 because you take 10% of 84 and then add it to 84, so 92.4, okay? Okay, but there's different approaches. One way you can approach this is find the new densities, because what happens when things heat up, their density changes. We haven't really called attention to that, but that's absolutely the case. You know, as I heat up lead and the volume expands, but the mass is unchanged, obviously, right? It's still the same mass lead, and I can find the mass lead taking the density that you look up for, because this is the density of lead at a particular temperature, right? It's at 20 degrees, right? When you look at densities, you don't think of them as being calibrated at a particular temperature, but they are, and that's relevant now, okay? So they're all assumed to be at 20 degrees Celsius. So then if I'm heating it up, then that means the density of the substance changes. Of course, eventually the substance will undergo a phase change, but we're not concerned about that right now. We're just concerned about it changing in density because it's heating while maintaining constant volume, okay? So that's one thing you could absolutely do here, is you could just find out the density changes and then find out the densities that then would change your sum of forces so that you actually have the correct amount submerged. That's definitely one approach you could take. I'm going to take a slightly different approach, you'll see. Same idea, but just, just setting it up mathematically a little bit differently. All right, so in part B, I'm going to set it up right away as a percent difference formula, okay? And it's nice because I can just carry through in a single formula, but it's kind of complex as an upfront step. So the idea here is I have the volume of heated submerged over the volume of heated lead minus the volume of submerged over volume of lead divided by the volume submerged over volume lead equals 0.1, right? So why is that? Well, because this is the new ratio minus the original ratio divided by the original ratio. Well, that's a percent difference. All right, that's the formula for percent difference. And if I want to set that equal to 0.1, then I'm going to, that's going to give me the correct value that I'm looking for, that I was asked for in the problem, right? Okay, so a percent difference of 0.1, okay, or 10%, because I didn't bother to multiply it by 100, which then would have made this equal to 10. Okay, so that's the idea. Let's label a couple things here. Right, so this is just the new fraction minus the old fraction divided by the old fraction, which equals the change in fraction. Okay. Furthermore, this is the 10% increase. All right, just shown here as a fraction rather than a percentage. Okay. So hopefully that makes sense as a setup. And again, remember this: all those terms submerged over object are just the same as what we found in part A. Okay. All right. So then we're going to go ahead and carry on to the next step. I've just circled this in green to show that this is the same term, but now I'm working on this term, these heated terms, because I don't have to do anything with the submerged over lead term, all right? So instead, I go over here and I say, okay, well, if I'm going to be expanding both, or I'm heating up, I should say, I'm heating up both the lead and the mercury, they're both going to expand, okay? All right? And so that means the volume of the fluid expands, which is this term right here. That's why I have the coefficient of volumetric expansion, of thermal volumetric expansion for the mercury right here with the subscript M denoting mercury. And then when you heat up the lead, it also expands volumetrically, which is why we have 3 times alpha L, L for lead, okay? So they're both going to expand, all right? Which is why, both those volumes will change. And notice, I say here, and this works because both the displaced fluid and the object expand, but at different rates. Furthermore, the reason we could even ask this question, ask for an increase, is because which one expands faster? The mercury, right? Because even once I multiply alpha by 3, so to get beta of lead is 3 times alpha of lead, it's still going to be about 9, right? 9 times 10 to the negative 5 inverse Kelvin, okay? And that's in comparison to mercury, which is 18. So in other words, mercury expands for a given temperature change twice as quickly as lead expands. So that means the density of the mercury is decreasing at twice the rate that the density of the lead is decreasing. What does that mean? That means that the lead will continue to sink further and further into the mercury, because effectively there's less and less pushback from the mercury as its density decreases. Okay? Now sure, the density of the lead is decreasing too, but not as fast. Okay? All right, so then we'll just go ahead and follow it through. Since submerged and object are going to cancel out, okay? So basically these terms all cancel out, all right? And so because we're just looking, we're looking for, so these are all the same term, right? I can factor it out of the problem. You see that? Because this term is equal to this term. They're all equal to each other. So I've just excuse me, I'd factor out a V submerged over V lead, right? Which then would just leave this term minus 1 over here. And then you see that it just cancel out, okay? That's where the cancellation comes from, okay? All right, and so then the whole thing cleans up into just this expression here, right? Where we don't, it's almost like the buoyancy is gone. We're just interested, of course it was set up by the buoyancy, but we're just interested in basically the values of temperature change, which is what we're gonna solve for, and then the actual coefficients, all right? And then the fact that it was, after all, a 10% increase, so that value shows up there. All right, so let's carry it through, all right, do some algebra, and eventually isolate my change in temperature, okay? And there's the final step. So then my change in temperature is going to be the fractional increase divided by basically the change in the coefficients, but the way we factor it out, that's where the 3.3 comes from, because you distributed in the 1.1, okay? All right, and so there we go. This is our answer. 11,090 Kelvin, which is also equal to a temperature change of 11,090 degrees Celsius. All right, so still not 11,000, 1,190. All right, so in other words, you'd have to heat up the system by 1,190 degrees Celsius in order for the lead to be sitting 10% lower, floating 10% lower in its mercury lake. All right, now would lead melt before you got there? Well, you got to find the melting point of lead. But regardless, we have that this is how we be able to see the effects of thermal expansion on a system like buoyancy. Okay, all right. Well, I hope that's interesting. And I hope the overall lecture has been interesting and informative, and thank you so much for watching.